Okay, so we're going to go through the Kirchoff's law problems. So Kirchoff's voltage rule. So for a closed circuit loop, the total voltage drop equals the total voltage rise. So what that's saying is, in a loop of a circuit, however much voltage enters that circuit, by the end of that loop, all that voltage must be used up. So if you started with 10 volts, at the end of the circuit, you'd have to have 0 volts before you get back to the power supply again. We talk about a loop. A loop refers to any part of the circuit where you can make a complete path from start to finish. Right, and then we'll show you how to use Ohm's law later on today. So here's an example. All right, so let's say this voltage has a value of 10 ohms. Okay. So we're just going to call this one, or sorry, 10 volts, not 10 ohms, 10 volts. Right. Well, as it goes through this, it has to spend that voltage in this resistor, and this resistor. And when we get back to here, the voltage has to be 0. All right. So the voltage rise 10 must equal the voltage spent. We're spending it in V1, V2, V3. These 3 resistors are spending that 10 volts. And when we get back to here, our voltage ends up being 0. Okay, so that is what Kirchoff's current law is saying, or a voltage loop rule is saying. Okay. Let's take a look at a practice problem. So let's assume that the battery has a voltage of 10 volts and each resistor has the same value. How much voltage does each resistor receive? Okay, so what we're going to do is we're going to first draw a loop in our current. And look, it even kind of shows it down here that the current is going to the left down here. So we can assume that the current is going clockwise. Right? So Kirchhoff's law says that the voltage gained, okay, which in this case is 10, has to be spent by these 2 resistors. Now here's the thing, we know that these 2 resistors have the same value, all right? So they are both going to spend the voltage equally. So we can call them both X. All right? And then we know that this whole thing has to equal 0. So if we solve for X, all right, which ends up being the voltage, we would get 5 volts each resistor. R1 has 5 volts, R2 has 5 volts. Okay. All right, let's try another one out. Up. In this next problem, same setup, but this time the voltage is 30, and then R1 has twice the resistance as R2. Okay, so twice the resistance is R2. Okay, so here we go again. All right, we draw our loop. In this case, we see that the loop is going, okay, again, it's going clockwise. So now it's 30, okay, equals. Now this has twice the resistance. So we're going to call this 2x, and then R2 is just x. Right? And we're setting this up a little differently than the one before. And the one before, it was the initial voltage minus all the other voltages equals 0. I skipped that step and kind of just said the initial voltage is on the left side of the equal sign. And then it's equal to all of the resistance gains in voltage. And this really should be 2x plus x, because these two add together to spend that voltage. So this gets us 30 equals 3x. And we solve for x, you would get 10 volts. But we have to go back. If we plug that in for x, that means R2 gets 10 volts. Yikes, 10 volts. But R1 is 2x, or 20 volts. Okay. So same idea, right? We just took another level because we have resistors of different values. Okay, so now we're going to do this next one. So now it's a parallel problem. Assume the battery has a voltage of 100 volts and R1 has a value of 10 ohms and R2 has a value of 40 ohms. Okay? So find the current in each resistor, find the voltage in each resistor, and find the current across the battery. So we're going to start by drawing out our loops. So we're going to draw 2 loops here. This is loop 1. This is loop 2. Actually, nope. Let me erase that. And then we're going to do this is loop 2. Big guy on the outside. So for this one right here, okay, we would have voltage, which in this case is 100. And we know that we're going to lose our voltage over R1. Now, here's the thing. We don't want to just write 100 minus R1. That doesn't really make any sense because we're looking for current. Well, we know this, that we can say voltage equals current. We're going to call this, all right, call this I2, right? This is I2. I2 times R1. Okay. And we'll do the same thing for this one. And the current going here, we're going to call this one, this current I3. Okay. And here we would have 100 minus I3 times R2. And both of these equations equal 0. All right, let's change up our color. All right. So I'm going to bring this, we're going to do this one up here. All right, so I have 100 equals, all right, I'm going to bring this I2 R1 to the other side, and I know R1 has a value of 10. So I have I2 times 10. And if I solve for I2, I get 10 amps. All right, I'm going to repeat and do the same exact process. Right, same exact thing, 1 sec. Okay, for this problem right down here. So now I have 100. Again, I'm going to bring that I3R to the other side. I'm going to call this I3 times 40. Because we know R2 is 40. If I solve for I3, I get 2.5. Okay, so find the current in each resistor. We did that 10 amps through R1. R2 is 2.5 amps. Find the voltage in each resistor. Well, that we know already, it's 100. How do we know it's 100? Because in each loop, loop 1, this one right here, and then this loop right here, this overall big one right here, okay? Each resistor is hooked up to this same voltage source. So the voltage rise, which is 100, has to be equal to the voltage drop. So if this is 100, then R1 has to have 100 volts applied to it. Okay. If this is 100, then R2 also has 100 volts applied to it. All right. So that's how we know that they're both 100. Find the current across the battery. Okay. So I'm going to erase this and just redraw a couple little things here. Okay. So here's what we said. We called this current I2. And we said it was 10. And we called this one I3. And we called this one, or not called, this was 2.5. All right, so we're going to now use that last thing we learned about, which was from before, how current gets applied to this. Well, we know that Kirchoff's current junction rule is all of the current going in must be equal to all of the current going out. Well, the current going across the battery isn't I2 or I3. It's a different current. It's some new current. And we're going to call this one I1. Okay. Well, here's our junction right here. Well, what's going into this junction? I2. And so is I3. And they're going to equal I1. So you can write at that spot, I1 is equal to I2, and I3. Well, if I1 is what we're looking for, we just plug in what we just found out. We know I2 is 10. Yeah, I cannot write tens apparently. And we know I3 is 2.5. So if we add them together, we get 12.5. So what is the current across the battery? 12.5. Okay. All right. So what I'd like you guys to try is this last problem. All right, find the current in each resistor, find the voltage across each resistor, and find the current across the battery. So make your two loops. All right, one loop is in the left side. You have a loop in the right-hand side. All right, set them up with V equals IR, and you're going to find out the current in each resistor. Once you find out the current, you can find the voltage in each resistor. All right, and then after that, you can do Kirchoff's law of currents, and you can take your two currents, you can add them together to get the final current across the battery. All right, have a good day, guys.